In this video, we will be looking at force as a vector. So first of all, we know that we can add two or more vectors and we get this resultant vector. So we can actually add two or more forces that are acting on an object. And the resultant force is a single force that produces the same net effect as the individual forces combined. Now, examples of forces can be a push or a pull of an object. For example, pushing an object on a rough surface, or the pulling of gravity on a falling object. Now, forces are measured in newtons, and 1 newton is equal to the force required to accelerate 1 kilogram of mass at a rate of 1 meter per second squared. Now, every planet has a different gravitational pull on an object. On Earth, that gravitational pull is 9.8 meters per second squared. So the force of gravity on a 1 kilogram object is 9.8 newtons. So we're multiplying the mass of the object by that acceleration due to gravity. So let's say we want to find the force of gravity on a person with a mass of 50 kilograms. Let's say this person is on Earth, where the acceleration due to gravity is 9.8 meters per second squared downwards. To find the force, the magnitude of that force, I'm going to take the mass in kilograms and multiply it by 9.8. And when I do that, I get 490 newtons. So that is the downwards force. On the moon, the acceleration due to gravity is 1.6 meters per second squared downwards. So to find the force here, that gravitational force, we're going to take 50 and multiply it by 1.6, and we will get 80 newtons. So that is just important if you have an object and you want to talk about that downward force acting on it. Now let's look at our first proper example. 2 tractors are being used to pull a tree stump out of the ground. The larger tractor pulls with a force of 3,000 newtons to the east, and the smaller tractor pulls with a force of 2,300 newtons northeast. Find the magnitude of the resultant force and the angle it makes with the 3,000 Newton force. So let's start with a diagram. Let's say this is the tree stump, and there's one tractor that is pulling with a force of 3,000 newtons to the east. So let's say this is the first one. And then we have another one with a smaller force, and it's going to the northeast. So I'm just going to draw a little compass. Northeast is exactly halfway between north and east. So that's going to be at a 45-degree angle. This is 45 and this is 45, but this angle is more useful. And there's the force. And I want the resultant force. Now my vectors are positioned tail to tail, so I am going to use that parallelogram law. So I'll draw a parallel force there, a parallel force there. We're going to start at the tree trunk and go diagonally. And this is my resultant force. Now, I know this side length must also be 2,300 newtons. And this angle here must be 180 subtract 45, so 135 degrees. And again, that's because when you have a parallelogram, 2 adjacent angles have to add up to 180, because the entire shape itself, all the angles have to add up to 360, and opposite ones are equal to each other. So this must also be 135, this must also be 45. So together they must add up to 180. All right, now we're ready to go. I want the magnitude of my resultant vector and the angle itself. I'm going to start with the magnitude. And I know I'm going to use cosine law here because I have the 2 sides and that contained angle of 135 degrees. And I will just jump straight to the square root of the two forces squared minus double those two forces, and then cos of the contained angle. And we can punch that into our calculators all in one go, and we get 4,903.9 newtons. So now that I have that magnitude, and I'll label it in my diagram, that has opened up a full pair between the magnitude and the angle of 135. So then I'm going to solve for this angle here, which pairs up with the 2,300 Newton force. And I'm solving for that angle because it asks us for the angle the resultant makes with the 3,000 Newton force. All right, so that's going to be 4,903.9 all over sine 135, and that's equal to the other incomplete pair, like so. And now we can cross multiply. And I am solving for an angle, so I know I'm going to have to take a sine inverse at the end. Okay. And I'm going to divide both sides by 4,903.9 to cancel that out. And I'm going to take sine inverse of this entire fraction. And when you do, you get 19 degrees. So therefore, the resultant force is 4,903.9 newtons, 19 degrees above the 3,000 Newton force. If it hadn't specified that it wanted the angle with the 3,000 Newton force, I could use a quadrant bearing and say north 71 degrees to the east, because that would be this angle here. Or I could use a true bearing of 71 degrees, that would work as well, but it was specified in the question. Moving on, a sleigh is pulled by a rope with a force of 180 newtons. If the rope makes an angle of 20 degrees with the ground, determine the force that pulls the sleigh forward and the force that lifts the sleigh up. So in this case, we're actually given this resultant force. This is the overall, that 180 newtons is the overall force that is being applied to the sleigh to pull it forward. But there are two forces that actually create this motion. So we're actually breaking this force down into two components, a horizontal and a vertical one. So I'm going to say this is my sleigh here, this is the ground, and the resultant force is this one here. 180 newtons makes an angle of 20 degrees with the ground. Now I need a force that's pulling the sleigh forward, and I need a force that's pulling the sleigh up. And there we are. And we can assume we have a right angle here. I'm going to label this the horizontal force and this the vertical force. And because we have a right triangle here, we can just use some nice SOHCAHTOA. I'm going to start off by solving for the horizontal force, which is adjacent to 20. So that is going to be cos, because the 180 is our hypotenuse. So the magnitude of the horizontal force divided by 180. And when I cross multiply, I'm just going to have 180 times cos of 20 degrees. And we get approximately 169.1 newtons. And I'll do the same thing for the vertical force, but this time I'm looking for the opposite side. So I'm going to use sine. Although we could have found this side length using Pythagorean theorem as well. But I like to do this, that way I'm using original information from the question and not using a rounded answer. But either way would be fine. And if we punch this into our calculators, we get 61.6 newtons. Therefore, a 169.1 Newton force pulls the sleigh forward, and a 61.6 Newton force pulls it up. Let's look at equilibrium now. Sometimes you can have multiple forces acting on an object, but the object does not move. And when that happens, we say the object is in equilibrium. And the sum of all of the forces acting on an object is the zero vector. So let's look at this little example. I have two forces here that are acting on, let's say, point P. Let's say our object is there. The resultant force would be this force right here, from P to A. If, however, there had been a third force acting on this object going in the opposite direction of this resultant, so right over here, same magnitude, just in the opposite direction, then these three forces, F1, F2, and this negative F, or this equilibriant force, they would add up to 0. So here's force 2. I'm going to put force 1 here. And here is that opposite vector of the resultant, which we can call the equilibriant force. So I'll just put E like this. If you look at all three of these forces, and if all three of them were acting on an object, the sum is 0. And in that case, that object would not move at all. So if we do have multiple forces, and we want to find that force that counteracts everything, and we're looking for the equilibriant force, we can find the resultant, keep its magnitude, but change its direction. Now, in order for you to see if it's possible for forces or an object to be in equilibrium based on the forces that are acting on it, we have to satisfy the following condition. If you have three forces acting on that object, if you take two of them and add them up, the sum has to be greater than or equal to the third one. And this has to work for any combination of the forces you have. So let's take a look. 3 soccer players kick a soccer ball at the same time. One player kicks with a force of 200 newtons, the other 300 newtons, and the third 600 newtons. Is it possible for all 3 players to kick but for the ball to remain unmoved? So let's say I pick the 200 and the 600. Well, those add up to 800, and that is greater than 300, so that's satisfied. If I pick the 300 and the 600, that's 900. That's greater than the 200. But if I take the 200 and the 300, they add up to 500. That's less than 600. That's not good. So this scenario cannot be put into equilibrium. The ball will move. And the reason we use this criteria, this one right here, is just to see, can these 3 forces form a triangle? So if 200, even if I lay them flat out like this is the 200, this is the 300, the 600 is going to be too much, even if it's going in the exact opposite direction. I can't connect to these vectors head to tail to have that 0 vector. So this, it's not possible. If, however, instead of 600 we had 500, then sure, it's possible. Or if it was less, like 400, that would be possible. You could create a triangle out of it. But this, it's not possible. Therefore, the ball will move. No equilibrium here. Final example. A 52-kilogram acrobat is hanging from a hoop that is held up by 2 ropes that make angles of 45 degrees and 40 degrees with the ceiling. Determine the tension in each rope. Okay, let's start off with the information that's given to us. The acrobat is 52 kilograms. That's their mass. One rope is held up by a 45-degree with the ceiling, the other 40 degrees. Now, there are no forces here, but we do have 3 forces that come into play. The first 2 are the tensions in each rope. So we have one force acting on one rope toward the ceiling, and then another one this way. Then we have a force for the acrobat itself. There is that downward force due to gravity, and that force is going to be the 52 kilograms times that 9.8. And if we do that, we get a force of 509.6 newtons. So we have our scenario here, but these forces are not arranged in a way for us to solve for any of the missing information. Now, although it's not specified in the question, these 3 forces must be placed in equilibrium because the acrobat and the hoop, they're not moving. They're not falling down. They're not being pulled up to the ceiling. That hoop is static. So the scenario must be in equilibrium. So I need to take these 3 forces and arrange them in a way so that the resultant force is 0. And in order for the resultant force to be 0 and for me to arrange them, they have to be arranged head to tail. So I'm going to start off, I'm choosing to start off with this gravitational force. So I'm just going to draw it. Here it is. Here's its force. Then I'm going to take the first tension rope, this one here, and I'm going to take its tail and I'm going to drag it to the head of the gravitational force. So here it is, and I'll just call this tension 1. Okay. Now I am going to put the imaginary ceiling here just so I can get the angle in place. Now I'll take the second rope, and again, I'm going to take the tail and I'm going to line it up with the head of the force I just put in, because everything has to be lined up head to tail. And there we are. Because the forces are in equilibrium, tension 2 should line up with that gravitational force. And again, I'll draw a little ceiling here and draw the 40 degrees, just like it was positioned in our original diagram, to the left of the rope. All right, now I can use a Z pattern to bring the 40 degrees right in here, which means that this overall angle is 85 degrees. I also know that the 40 degree with this one here are complementary, so 90 minus 40 will give me 50 for this inside angle. And then I can use my 180 rule to get the final angle, and I will get 45 degrees. Now I have all 3 angles in my triangle, and I am just looking for the missing 2 sides to find the tension in each rope. So I'm going to do a sine law because we do have that nice full pair between the 85 degree angle and the 509.6 force. So here's my full pair, and I'm going to start off by finding the magnitude of the tension in the first rope, and that's directly across from the 50 degree. So now I'll cross multiply, and this time I am solving for a side length, not an angle, so I'm not going to be taking a sine inverse at all. I can just divide by sine 85. And when I do that, the magnitude I get is 391.9 newtons. And now we can repeat the process for tension 2. So I'm going to use the same full pair, but the second rope is across from the 45 degree angle, and once again, cross multiply. And we'll divide out that sine 85 to cancel it out here. And now, if we go to our calculator, the tension in the second rope will be approximately 361.7 newtons. So then we can write our therefore statement. Therefore, the tensions in the ropes are 391.9 newtons and 361.7 newtons. And again, the diagram here came from the fact that the hoop wasn't moving, so we can assume that the forces are in equilibrium to keep the hoop and the acrobat in place and not falling down or lifting up by the ropes.